Binary search tree. A binary search tree is a binary tree that satisfies binary search property. What is a binary tree and what is this binary search property that converts a binary tree into binary search tree? Let us understand this. First of all, binary tree. We already discussed binary tree in multiple lectures. What is a binary tree? It is a tree in which each node has at most two children. So that means each node can have 0, 1 or 2 children. So if this is your node, root node, let us say it has 2 children, it is still a binary tree. If this child again has 1 child, it is still a binary tree. If this has again 2 children and if these children do not have any children, this is still a binary tree because if you see any node in this tree, each node will have either 0, 1 or 2 children. None of the nodes will have more than 2 children. This is a binary tree. Next question is, what is the binary search property? This is what converts this binary tree to a binary search tree. So the binary search property, it has two conditions. The first condition is for any node in the tree, all the values that are present in the left subtree of that node, let us presently consider this node, the root node, all the values that are present in the left subtree of that node should be less than or equal to the value of that node. And the second condition is that all the values that are present in the right subtree of that node should be greater than the value of the node. So this is the condition for binary search tree. This is what you call as binary search property. The property says, so it is not just for the root node, it is applicable for any node. If you see this node, or let us say if you see this node, the same condition applies here as well. Whatever nodes are present in the left subtree, they should be either less than or equal to the parent node. Whatever nodes are present in the right subtree should have values greater than whatever is the value of parent node. So this should be valid. This property should be valid for any node in the tree. If it satisfies for all the nodes of the tree, then you call it a binary search tree. Okay. So this is the property of binary search tree. Then the question is, why do you want this binary search tree? What is the speciality of this binary search tree data structure? So the major requirement is it is very efficient for searching, insertion and deletion. If you want to search some element in this binary search tree, because of this binary search property, searching any particular element in the tree becomes much easier, because in a normal binary tree, you will have to go through the complete tree by doing, let us say, pre-order traversal, in-order traversal or post-order traversal in order to search for an element. But in case of binary tree, it is much easier. You can directly search for an element and find out. Even if it is a heap, you will have to do complete traversal if you want to search for something in the tree. But that's not the case with binary tree. That's the first thing. And one more thing is, and same is the case with insertion as well as deletion. So when we go to the lectures on how to search, how to insert, how to delete all those on binary trees, you will understand that how easy is it to insert a new element, how easy is it to remove an element and so on. So next thing is binary search tree. It has a peculiar speciality, and this peculiar speciality is that for any binary search tree, if you do in-order traversal of that binary search tree, you will get a sorted list. It will be ascending sorted list. So if this is your binary search tree and you do an in-order traversal, the list that you get will be sorted in ascending order. So I'll just show you with an example. If you take any random tree, let us say 50 is here. This is a binary search tree. Okay, so whatever is in the left side should be lesser than 50. So consider something like 41. 41 can be here, and here something should be larger than 50. So 60 can come here. Whatever comes to the left side of 60 should be smaller than 60 because it is in left side. Also, it should be larger than 50 because it's in the right side of 50. So let us say this is 58. And maybe you have one element here, it should be smaller than 41, let us say 30. So if these are your elements, then if you do in order traversal on this, you will get a sorted list. How do you do in order traversal? As we learned in the in order traversal lecture, start from here and note down the element whenever you visit it for the second time. So first time, first time, first time, second time you are visiting 30. So write down 30. Again you continue, third time, second time you visited 41, write down 41. So what am I doing? In order traversal of this tree. Third time here, second time on 50. So write 50. Again I'm traversing first time, second time. So write 58. Again traverse through it, second time 60. So I am writing down 60. Go on, third time, done. So see this list. Whatever list I got from the binary search tree, this is a sorted list. So this is a speciality of binary search tree. If you simply do in order traversal of the binary search tree, you will get a sorted list of whichever elements are present in the binary search tree. Next question is, what all are the different applications of a binary search tree? Why should you build a binary search tree? We already said speciality is that searching is very efficient, and we also know you'll get sorted order directly if you do an in order traversal. So where would you actually use this? So one use would be in, let us say, databases or file systems where you want to do efficient searching. If you have huge database and you want to search for something, it will be easier if you use binary search tree. That is why in the name itself you have binary search tree. It makes searching very efficient. And another thing would be that if you are maintaining some databases, dynamically you can add or delete easily in a binary search tree. At the same time, binary search tree also comes with some disadvantages. Major disadvantage is that the height of tree could go to order of n. What happens if height of tree goes to order of n? We know many of the tree operations are dependent on the height of the tree. So with binary search tree, if you inserted one element, next element, let us say, is smaller than that, then you inserted another element which is even smaller, then this tree will just grow directly downward. So the height of tree will keep increasing. In that case, many of your tree operations will go to order of n. That is, whichever operation is dependent on the height of the tree, that will go to order of n. So this is one drawback of binary search tree. What do you do then? If there is a drawback, you have to find some solution. And the solution is balanced binary search trees. There are some particular binary search trees which come under the category of balanced BSTs. So the balanced BSTs, they have a speciality that their height will never grow directly downwards. It will always be balanced, and generally you will be able to maintain a height of order of log n in all the balanced binary search trees. So after we complete all our detailing lectures on binary search trees, we'll also learn about balanced binary search trees. There we'll learn about different trees like AVL trees, or maybe AVL trees, B trees are there, then you have B plus trees, you have red black trees. So we'll learn about all these different types of binary search trees which are balanced binary search trees. So these search trees are even more efficient than a normal binary search tree. But what you have to understand is, many times you won't implement all these. You would directly go for a normal binary search tree. The reason is, implementation of a binary search tree is much easier compared to that of a balanced binary search tree. So in most of the normal cases, you would directly use balanced binary search tree. So in algorithms course, the trees that are most commonly used would mostly be binary search trees, right? So in the coming lectures, we'll go in detail into how exactly can you search, insert, delete, and so on.